Good morning. Today I am going to deal with the decarboxylation reaction. There are two different methods for decarboxylation reaction. Which first one is action of soda lime on sodium carboxylates. When the sodium salt of an aliphatic saturated monocarboxylic acids fused with the soda lime, an alkane with one carbon atom less than the parent carboxylic acid is obtained. What do you mean by soda lime? Soda lime is a 3:1 mixture of sodium hydroxide and calcium oxide. So in effect, the reaction involves the removal of a molecule of carbon dioxide from the carboxyl group of the acid. So it is called decarboxylation. This is our sodium salt of carboxylic acid, that is sodium carboxylate, RC double bond O, O, Na, fused with the soda lime, sodium hydroxide and calcium oxide. It will convert it into alkane, RH, and Na2CO3 group getting eliminated. That is decarboxylation reaction. In total, here carbon dioxide molecule getting eliminated from carboxylic acids. So it is called a decarboxylation reaction. For example, sodium acetate, CH3, C double bond O, ONA, sodium acetate, heating with the soda lime, it will convert it into CH3H, that is CH4, that is our methane, plus sodium carbonate. What is the mechanism of decarboxylation reaction? Here, carboxylate anion. We know that the reactant is sodium carboxylate. So, the carboxylate anion easily eliminates one molecule of carbon dioxide. This negative charge will shift to this bond and R group getting eliminated as R minus. So we get R minus plus C double bond O double bond O. That is our carbon dioxide. We get carbanion. This carbanion treated with the H plus to form alkane, RH. When the reaction started from free acid, that is our RC double bond O, OH, that is free acid. This is sodium carboxylate anion. Here free acid, it will, here hydrogen leaves as H plus and it will convert it into RC double bond O minus and H plus. This carboxylate anion easily eliminates carbon dioxide, R minus getting eliminated, R minus and CO2. This R minus reacts with the H plus to form our alkane RH. That is the mechanism of decarboxylation reaction. Important thing about decarboxylation is here one carbon less compared to the parent acid. For example, here the number of carbon in the case of sodium acetate is 2. The resultant product contains 1 carbon. So here number of carbon decreased by 1 unit. Okay. Second reaction is very important reaction, that is our coal-base electrolysis. Here a concentrated aqueous solution of sodium or potassium salt of carboxylic acids on electrolysis gives an alkane containing even number of carbon atoms at the anode. This process is called coal-base electrolysis or coal-base electrolytic method. We have another reaction, that is coal-base reaction. Another module in this paper, that is not coal-base electrolysis, that is coal-base reaction. Both reactions are different. Don't get confused with each other. Here sodium carboxylates undergo hydrolysis to form alkane and carbon dioxide getting eliminated. 2 moles of carbon dioxide CO2 getting eliminated. 2 moles of NaOH. Here NaOH is formed due to aqueous solution of sodium salt of carboxylic acid is used for electrolysis plus hydrogen. What is the mechanism of coal-base electrolysis? First step is ionization. We know that sodium acetate ionized into acetate anion and Na plus. Here 2 moles of sodium acetate reacts. So we get 2 moles of acetate anion. 2 CH3 C double bond O minus and 2 moles of Na plus. That is the first step, ionization. Then what are the reactions at anode and cathode? At cathode, alkane will be evolved. What is the mechanism? The intermediate present at anode is free radicals. Here 2 moles of CH3 C double bond O minus acetate anion leaves 2 electrons converted into 2 moles of acetate radical CH3 C double bond O radical, or 1 mole of acetate ion eliminates one electron. If this oxygen eliminates one electron, what will happen? It will convert it into radical. That is CH3, C double bond O, O radical. So here two free radical moles are producing. Then it will easily eliminates carbon dioxide molecule. This is a free radical reaction. This free radical shifts to this bond, and here this bond indicates the presence of two electron. That is CH3 and C double bond O connecting with the two electron. That is a single bond. From this two electron, one electron shifts to this bond and one electron shifts to carbon. That is, the resultant product is 2 moles of CH3 radical, and when one electron shifts to this bond and one electron shifts to this bond, that is again 2 electron, which means a bond, another bond present in between C and oxygen. So that is our carbon dioxide. 2 moles of carbon dioxide getting eliminated and 2 moles of CH3 radicals also produced. This half arrow represents free radical mechanism. This half arrow represents the flow of one electron only. Completed arrow represents flow of two electrons. Free radical mechanisms represented in this manner. Here we use only half arrows. Then the final step is dimerization reaction of free radical. 2 moles of CH3 radical getting combined or dimerized into our ethane. So ethane will evolve at anode. At cathode, water molecule adds with the electron converted into OH minus and H radical. Then H radical dimerization step converted into hydrogen gas. So at cathode, hydrogen gas will evolve. At anode, ethane gas will evolve. That is about coal-based electrolysis. Another important reaction is action of heat on dicarboxylic acids, and it is also called Blanc's rule. Blanc is a scientist who found this reaction. In 1905, Blanc found that the products of action of heat on dicarboxylic acids could be monocarboxylic acids, cyclic anhydrides or cyclic ketones based on the relative positions of the two carboxyl groups or the number of intervening carbon atoms. Let us discuss in detail. First case, dicarboxylic acids with 0 or 1 intervening carbon atoms, which means dicarboxylic acids in which carboxyl groups are separated by 0 carbon atom or 1 carbon atom. These type of dicarboxylic acids are involved in this category. When they are heated, it will decompose into monocarboxylic acids and carbon dioxide getting eliminated. For example, oxalic acid. This is the structure of oxalic acid, COH, COH, in which two carboxyl groups are attached to each other and there is 0 intervening carbon atoms, which undergoes decarboxylation when heated to convert into monocarboxylic acids. That is our formic acid. Another example is in the case of malonic acid. Malonic acid has one intervening carbon atom. Structure of malonic acid is COH, CH2, COH. When it heats, it will convert it into monocarboxylic acids. What will be the structure of monocarboxylic acid? CO2 group getting eliminated and it will convert it into CH3COH. That is our acetic acid. That is the first case, 0 or 1 intervening carbon atoms containing dicarboxylic acids converted into monocarboxylic acids. Next case is dicarboxylic acids with 2 or 3 intervening carbon atoms. On heating alone at 300 degrees Celsius or distill with acetic anhydride at 300 degrees Celsius, it leaves water molecule and converted into its anhydrides. For example, this is succinic acid, COH, CH2, CH2, COH. Here the number of intervening carbon atom is 2. On heating, it will convert red into succinic anhydride. 1 mole of water getting eliminated. Another example is in the case of glutaric acid. Here the number of intervening carbon atom is 3. When it heats, it will convert it into glutaric anhydride. Then last case is dicarboxylic acids with 4 or 5 intervening carbon atoms. On heating, at 300 degrees Celsius or distill with acetic anhydride at 300 degrees Celsius. Dicarboxylic acids with 4 or 5 carbon atoms between the two COH groups converted into cyclic ketone by leaving 1 mole of carbon dioxide and 1 mole of water. Here adipic acid COH, CH2, 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 COH. Number of intervening carbon atom is 4. When it heats at 300 degrees Celsius, 1 mole of carbon dioxide and 1 mole of water H2O getting eliminated and it will converted into cyclopentanone. So that's about in the case of 4-5 intervening carbon atoms containing dicarboxylic acids. So Blanc's rule can be summarized as when heated alone or when distilled with acetic anhydride at 300 degrees Celsius, 1,3-dicarboxylic acids yields monocarboxylic acids with loss of 1 carbon atom as carbon dioxide. 1,4 and 1,5-dicarboxylic acids yield cyclic anhydrides by dehydration and 1,6 and 1,7-dicarboxylic acids yield cyclic ketone with the loss of water as well as 1 carbon atom as carbon dioxide. This reaction is known as Blanc's rule.